Good day everyone. My name is Sachin Ahankari, working as assistant professor in Narasimha Reddy Engineering College in AC department. So today I will give the basic information about the OpAmp and some of the characteristics of OpAmp we will study. So here in the basic information, as you are aware that the power supply range for the OpAmp is ranging from plus or minus 5 volt to plus or minus 22 volts. So here in general we are preferring the power supply of 12 volt to 15 volt, that is plus or minus 12 volt to 15 volt in general, but you can apply from 5 volt to 22 volt. After 22 volt OpAmp may get damaged. So here this is the information about the power supply connection and power requirement, and we will see how the manufacturer's designation is there for linear ICs. So the Fairchild manufacturer of linear ICs, the Fairchild is going to use the notation of mu A and mu AF. In similar fashion, National Semiconductor is making the designation of LM, LH, LF or TBA. So the starting letters which are printed on the IC for the National Semiconductors are LM, LH, LF and TBA. After that few numbers are there like 741 and 555, like that. The numbers of the ICs are given, but starting it is written as LM, LF, LH, TBA in that fashion. So these are the manufacturer's designation. Just by looking towards the what is written on the IC, you can easily come to know that which manufacturer has manufactured this IC. So for Motorola MC, MFC, for RCA, CA, CD, for Texas Instrument, SN, Signetics, N oblique S or NE oblique SE. For Burr Brown, it is BB. So these are the manufacturer's designation for the linear ICs. So few of the manufacturers of 741 IC, that is OpAmp IC, is National Semiconductor, LM741, Motorola MC1741, RCA, CA3741, Texas Instrument, SN 52741, Signetics N5741. So the last letters, if you observe, are 741s here, and these are the OpAmp ICs, and these are the popular OpAmp ICs manufactured by the manufacturers like National Semiconductor, Motorola, RC, and Signetics and Texas Instruments. So we will see few of the characteristics of OpAmp. Here the characteristics or electrical parameters of the OpAmp, or they are also called as performance parameters of OpAmp. So few of the characteristics are input offset voltage, input offset current, input bias current, differential input resistance, input capacitance, open loop voltage gain, CMRR, output voltage swing, output offset voltage, average temperature coefficient of offset parameters, supply current, slew rate, and PSRR. It is also called as SVRR or PSS. So it is power supply rejection ratio or supply voltage rejection ratio, or it is power supply sensitivity. So these are the characteristics. So we will see the definitions one by one here. The input offset voltage, it is the voltage that must be applied between two input terminals of OpAmp to null the output. To make the output voltage 0, in between two input terminals we are applying some voltage, that is VIO. It is denoted by letter VIO, and this voltage is applied in between inverting and non-inverting input terminal of OpAmp to make the output voltage 0. So practically uh, uh, if the voltage is applied, similar voltage is applied, ideally the V0 should be 0, but practically some voltage is available at the output. To make that voltage 0, we are applying some voltage in between two input terminals, and that voltage is called as a input for offset voltage. So it is a voltage or differential input voltage that must be applied between two input terminals of op-amp to null the output, and it is denoted by VIO, and the value of input offset voltage maximum value is 6 millivolt DC, and VIO is given by VDC1 mod of VDC1 minus VDC2. Actually VDC1 through a series resistance RS, it is connected to inverting input terminal, and VDC2 if it is connected to the RS and it is connected to the inverting input terminal, VDC1 is connected to non-inverting input terminal, because the difference voltage is non-inverting input terminal minus inverting input terminal. Anyhow, it is a mod. You can connect it anywhere. You can connect it anywhere since it is a mod. So here, this is a definition of input offset voltage, and the next definition, if you go, input offset voltage, input offset current. So it is the algebraic difference between currents flowing into inverting and non-inverting input terminals of op-amp. So if I take IB1 as current flowing through the inverting input terminal and IB2 as current flowing through the non-inverting input terminal, then the difference between these two, or magnitude of difference between these two, is called as input offset current. So it is the algebraic difference between currents flowing into inverting and non-inverting input terminal of op-amp, and it is denoted by letter IIO, and generally the value of IIO is 200 nanoampere. So if the input offset current is greater than 200 nanoampere, then the op-amp is of no use. We are just going to throw out that op-amp outside, because the op-amp is damaged at that time. So input offset voltage must be less than your 200 nanoampere. So next electrical parameter or performance parameter or the characteristic is input bias current. So input bias current, it is the average of currents flowing into inverting and non-inverting input terminals of op-amp, and the value is IB1 plus IB2 divided by 2. So IB, it is denoted by IB, and it is the average of currents flowing into inverting and non-inverting input terminal of op-amp, and it is given by IB is equal to IB1 plus IB2 divided by 2, and the maximum value for IB is 500 nanoampere. So it is a maximum value for the input bias current. Now differential input resistance. So it is the equivalent resistance that can be measured at either inverting or non-inverting input terminal of op-amp with other input terminal connected to ground, and it is denoted by Ri. For 741C, it is the value is 2 mega ohm. So generally for the op-amp terminals, either to the positive terminal or to the negative terminal, ohm meter one terminal is connected either to the non-inverting or inverting input terminal, and the other terminal is connected to ground, and whatever the count is counted by your ohm meter, that count is called as differential input resistance. The value is 2 mega ohm here for the differential input resistance. Now if you go for differential input capacitance or input capacitance, so it is similar to differential input resistance. It is the equivalent capacitance that can be measured at either inverting or non-inverting input terminal with other terminal connected to ground, and it is denoted by Ci. Input capacitance is denoted by Ci, and the value of Ci is 1.4 picofarad as per the data sheet. So here generally the LCR meter is taken in order to measure the capacitance. So you are going to press the button of C, and so that it is going to calculate the value of capacitance. The LCR meter, one terminal should be connected to either to the inverting or to the non-inverting input terminal, and the other terminal of LCR meter is grounded, and whatever the count is counted by the LCR meter, or whatever the capacitance count counted by the LCR meter, that is called as the input capacitance. So generally it is 1.4 picofarad. Open loop voltage gain, so it is denoted by AOL. It is open loop voltage gain, or it is also called as a differential voltage gain also. So open loop voltage gain or differential voltage gain, both are same, and here it is a ratio of output voltage to the differential input voltage. So whenever the op-amp is connected in open loop configuration, that is without any feedback, then it is called as a open loop voltage gain, and the value of open loop voltage gain is very large value. Generally, typically it is 10 to the power 5 to 10 to the power 7. So here it is given as 2 into 10 to the power 5. So it is 2 into 10 to the power 5 for 741 IC. It is typically 2 into 10 to the power 5 for open loop voltage gain. Now next definition is CMRR, that is a common mode rejection ratio. The common mode rejection ratio is ratio of differential input voltage, differential voltage gain to the common mode voltage gain. So it is a ratio of differential voltage gain to the common mode voltage gain. So AD is differential voltage gain or open loop voltage gain. We know that the open loop voltage gain is 2 into 10 to the power 5 in general for 741 IC. The value of common mode voltage gain, ideally it should be 0, so that if it is 0, then CMRR should be infinite. Ideally, if AC is 0, then CMRR is infinite. So if you go practically, AC is having some small value and AD is having some large value, therefore CMRR is very large. So large value divided by some small value, therefore CMRR is very large. That's why CMRR is expressed in dB, and the value of CMRR in dB is 90 dB. The CMRR, higher the value of CMRR, better is the matching between two input terminals, and smaller is the output common mode voltage. So if the CMRR is high, better is the matching between two input terminals of the transistors which are at the dual input balanced output. So transistors are better matched, then the value of CMRR is very high. Also, if the value of CMRR is high, it indicates that it is having smaller output common mode voltage. Output common mode voltage, and if the CMRR is high, then it is having the better ability to reject the common mode voltages. The common mode voltages such as electrical noise, they are rejected in better fashion if CMRR is high, and you can use the op-amp in noisy environment if the CMRR is high. If the CMRR is low, then you cannot use the CMRR in noisy environment, and the value of CMRR is going to decrease with the frequency. As the frequency is going to increase, it is constant for some time, and after that it is going to decrease. So CMRR rejects the frequency noise signal at lower frequency in better fashion than higher frequency. So it will not reject the higher frequency noise, it will reject the lower frequency noise in better fashion. It will not reject the higher frequency noise it will not reject the higher frequency noise as that of your low frequency noise. So if the CMRR is high, then the op-amp has better noise rejection, and you can use the op-amp in noisy and industrial environment. The CMRR falls at higher frequencies. That's why op-amp cannot reject the noise at higher frequencies, and OpAmp rejects the noise at lower frequencies in better fashion than the higher frequencies. So this is about CMRR. So few of the other characteristics we will see in the next lecture. Thank you.